Alright, so this video is actually just to review a little bit. I already did this in class with some of you, but some of you were gone when we were going through these types of problems, so you might need this so you can figure out what's going on. So we're just going to go through some of the examples that were in the notes, and then I'll throw in a few extra examples for the worksheets that we're doing in class today. Otherwise, some of you have already done these parts, so you could skip ahead to where I'm doing some specific examples for the worksheets today in class. So just do what you need to do. Otherwise, we have specific types of problems that we're going to have to do now and in the future. So I'm either going to start you with grams or moles in these first examples. So whatever you're given, that's what you start with in a conversion factor. But the whole idea of this mole concept is that I know that 1 mole of aluminum has a mass that I can find up on my periodic table. Aluminum has this 26.98 mass on this periodic table. I believe on your periodic table it's 26.99. So I might actually just use that so it's not confusing, because you're supposed to use your planner. As long as everybody's using the same periodic table, these don't tend to change. But obviously an online version may be more updated, right? But if I use this mass for aluminum, 1 mole of aluminum has a mass of 26.99 grams, right? All I have to do is divide, and this should give me my answer for this problem, right? So I take 11.9 and I divide it by 26.99, or maybe it is 26.98 on your periodic table, I don't know. But just sounded wrong at first, so let's make that 26.98, because that actually does sound right now. I don't know why I changed it to begin with, but if I divide this, I end up with an answer of 0.44. I need one more sig fig because this 11.9 had 3 sig figs, so 0.441 moles. And simple, pretty easy. Otherwise, if I give you moles to start, 2.25 moles for a substance, I can find out how many grams that is, and all I do is the opposite of what I did before. Instead of dividing by a molar mass, I'm going to multiply by a molar mass, because 1 mole of iron has a mass off my periodic table as opposed to aluminum up above. That's why I have different numbers for different problems. I look for iron on my periodic table. It's 55.85 as a mass. So I multiply by that mass. Moles cancels. I get grams as an answer. 2.25 times 55.85 on my calculator gives me an answer of 125.6625, but I only need 3 sig figs again, so I'll round it to 126 grams of iron. So it's actually pretty simple. You use that mass off your periodic table, and you multiply or divide accordingly whether you want a mole answer or a mass answer. Right? If you're given moles, you can come up with grams of a substance. If you're given grams, you can tell me how many moles it is. So that's one type of example. This is another type of example. So using our mole concept in a different way, right, I can figure out how many moles of silver are in a sample that contains 3.01 times 10 to the 23rd atoms, because that was our other definition for a mole. 1 mole is always 6.022 times 10 to the 23rd of anything. So in this specific case, my label is atoms, but I can use a lot of different labels for that. Usually it's atoms or molecules for us, but on the worksheets I give you a lot of different things, like elephants or marbles or whatever. It doesn't really matter what it is, right? It's an abstract concept anyway. So why not have a mole of golf balls, right? That's a lot of golf balls. Enough golf balls that it would be larger than the mass of the earth if you put them all together. But you can use whatever label you want. It just needs to match, obviously, right? So I divide, I get rid of that atoms, I get moles instead. Also, my 10 to the 23rd cancels here, if you notice that. So if I take 3.01 and divide it by 6.022, I get an answer of 0.449833 whatever, right? It actually rounds to a 0.500 when I get 3 sig figs again, but that's going to be my answer in moles. Whereas this next one is just a flip again. If I start with moles, I can find out how many particles there are in that sample, right? So I want to know how many atoms of aluminum, right? So I know that I'm talking about a conversion here. 1 mole is 6.022 times 10 to the 23rd atoms of anything, right? So mole goes away. I multiply. I tack on my exponent. So first I take the 2.75 times 6.022. And I get an answer of 16.56. Again, 3 sig figs. I should call it 16.6 times 10 to the 23rd. But again, I should be careful because I learned last chapter that if I have the decimal in the wrong place, I need to move it. Since I made that smaller, I should make this bigger. Right, so my actual answer is 1.66 times 10 to the 24th atoms. Right, that's how many aluminum atoms would be in a sample that was 2.75 moles of aluminum. So again, same idea as before. I can either multiply or divide. Depending on what I'm giving you, you can get moles from atoms or vice versa. You can get atoms from moles. Whereas these last two examples just go through the whole gambit, right? I can start with atoms and I could come up with a mass, but I can't relate those two things directly, right? I can change my atoms, my 1.20 times 10 to the 8th atoms, into moles first, because 1 mole happens to be 6.022 times 10 to the 23rd of anything. So in this case, I'm using an atoms label, but that's just because I was given atoms. Otherwise, now I can change my moles into a mass, right? Because 1 mole of copper has a mass off my periodic table. I guess I went back here, but my periodic table, copper right here, has a mass of 63.55 grams. So moles went away, atoms went away, right? It's just a 2-step process. I have to change atoms into moles, then I can change moles into grams. So I just multiply and divide. So I can do that in whatever order I want. 1.20 times 63.55, and then divide by 6.022. Right, so that gives me part of my answer. Right, that's my 12.66 whatever. Right, but I also have this 10 to the 8th divided by 10 to the 23rd. That should be a subtraction. That means I have a 10 to the negative 15th power. Right? I also have to do a little adjusting there, so I have to move my decimal. Again, move it to the left. I have to make it bigger. So my final answer is going to be 1.2, round it, 1.27 times 10 to the negative 14th grams of copper. Notice that's a really, really small amount, right? That's so small that it's immeasurable, right? You wouldn't even be able to see this sample of copper. So although I had 1.20 times 10 to the 8th atoms, that's not very many atoms, right? I mean, it's a lot of atoms, technically, right? It's 120 million atoms, but that's not enough to make a sizable sample of copper, a sample that's big enough that you can even see it, let alone measure it, weigh it. So just putting this into context, right? Atoms are super, super tiny. Even if you had 120 million copper atoms, you wouldn't have enough that you'd even register the mass. You wouldn't even notice it. Otherwise, next one, if I have 4 grams of sulfur, I can change that into an atom amount, right? This is basically the flip of the problem before. I just work it backwards and flip things over. Right? Instead of multiplying by a molar mass, I'm going to divide by a molar mass, because 1 mole of sulfur has a specific mass. Specific mass off my periodic table is 32.06 grams. Whereas 1 mole of anything has 6.022 times 10 to the 23rd atoms in this case, right? So again, there's 2 conversion factors. One's always the same, because 6.022 times 10 to the 23rd is always the same number, whereas the other number is always changing, because there's a difference between copper and sulfur. They have different molar masses. You have to use different numbers off the periodic table, whereas the 6.022 times 10 to the 23rd is constant. That doesn't change, right? But I cancel my labels here, my units. I end up with the atoms as an answer. Again, I need to multiply and divide. 4 times 6.022 divided by 32.06. And then get an answer here. It's 0.75134, so I'm going to call it just a 1 because I only need 3 sig figs. And then I'm going to take that times 10 to the 23rd again. Now I have to adjust this in a different direction. I need to move the decimal here. That means I should subtract this time. And I end up with an answer of 7.51 times 10 to the 22nd atoms. Again, this is a big enough sample that it's actually measurable as 4 grams, right? It's not quite a mole, obviously, because a mole of sulfur would have been 32 grams. But it's still big enough that I can measure it. There's enough atoms there that I can actually measure it. So there's a difference between 10 to the 22nd and 10 to the 8th. That exponential difference is why one sample is big enough to measure, the other one's not. So those are all the different kinds of problems that you need to do, right? So in your worksheets, you'll have examples that look like this. Number 1, on the first worksheet, you're changing 2 moles of elephants into a number of elephants. Right? On that first worksheet, you're only going to use 1 conversion factor. It's always 1 mole equals 6.022 times 10 to the 23rd. The label changes. In this case, I'm going to use elephants. But otherwise, it could be atoms or molecules or marbles or golf balls or whatever it happens to be. But I'm going to take whatever I'm given, and then I'm going to use a conversion factor. I'm just going to put the mole wherever it needs to be. Right? In this case, I need the 1 mole to be on the bottom so that this cancels. Otherwise, I'm going to multiply by 6.022 times 10 to the 23rd. Again, I have an elephant label here. But on that whole worksheet, you're either multiplying or dividing by 6.022 times 10 to the 23rd. If you were given moles to start, you need to multiply. If you're given a huge number of something, you need to divide by 6.022 times 10 to the 23rd. So just use the appropriate conversion factor, flip this whichever direction you want so you can get an answer. And I don't really need a calculator for this one. It would be 12.044. I do only have 1 sig fig in that 2 moles, so I should round this to 1 sig fig. It'd be 10 times 10 to the 23rd. I do actually have to move the decimal, which actually makes it a 1 times 10 to the 24th. Be careful not to keep that 0, because I only wanted 1 sig fig anyway, right? There's 1 times 10 to the 24th elephants in 2 moles of elephants. Now, it's a nonsense question. There's no such thing as a mole of elephants. There have never been a mole of elephants on this planet. There will never be a mole of elephants, even if you counted all the ones that are alive and had died in the past. Right? That's a huge number of elephants. Again, so many elephants that the mass, if you put them all together, would be much larger than the Earth. It'd be more equivalent to the size of a star, like our sun. So, not realistic, but you could do this for any kind of problem. So you're always going to multiply or divide by 6.022 times 10 to the 23rd on the first worksheet. Second worksheet is different, right? On this one, I'm always going to use a molar mass. I'm going to have 1 mole of substance is equal to a given mass, but this mass is not constant. It's always changing. It depends on what elephant I'm talking about. I got elephant on the brain, so I can't stop saying it, right? For lithium, I have a specific mass off the periodic table that I'm going to use. It happens to be 6.94 grams, right? But I could also do any other elephant that's on the periodic table. So you just gotta be a little bit flexible, right? But it's the same idea. I had that 6.94 that I'm going to use in this case. I may multiply or divide by that mass that I found on the periodic table. In this case, because I started out with 5 grams, and I need to have the same label here as up here, I need to divide by my 6.94 grams to get my mole amount. Right, so I just do what I gotta do. 5 divided by 6.94 gives me a 0.72. Again, I actually only need 1 sig fig, so I just call it 0.7 moles. And there you go. I'm done with that one, right? Otherwise, on your next one, if you were given moles and you want grams, you multiply by a molar mass. But that molar mass always changes. It's not the same thing. You got to use your periodic table for this. So that's the whole second worksheet. Same things over and over again. You're just practicing it. Third worksheet. Right? If I'm given atoms, I can't go to grams directly. But I can change atoms into moles, and then I can change moles into grams, or vice versa. If I started with grams, I could turn it into moles, and I could turn moles into atoms. Right? Those last 2 problems we did in the notes, that's what these are. Right? You have to do 2 conversions every time. Since I started out with a really big number of atoms, first thing I'm going to do is divide by Avogadro's number. Because that's how many of anything, including atoms, are in a mole. Whereas the second conversion, I'm changing moles into grams. So I should put the 1 mole on the bottom because that's where I need it to be now. I need to look up that specific element. I know what it is. Carbon's 12.01. But look for it on your periodic table so that you have that number you need. 12.01 grams and 1 mole. So I should be able to multiply and divide now, right? 5 times 12.01 divided by 6.022 gives me an answer of 9.97. Right? I actually only need 1 sig fig again. So that's not typical. But on this worksheet, I might have done that a lot. So it started out as 9.97. I got to round it to 1 sig fig, which is a problem because it actually turns the answer into 10, which if you kept a decimal would have 2 sig figs. But it's that number times 10 to, let's see, 26 minus 23, the third power. Again, this is not an appropriate answer unless I adjust things. If I move the decimal, though, I got to get rid of that 0. It's 1 times 10 to the 4th power as an answer. That's how many grams of carbon I would have if I had that many atoms to start, right? So you could also take this out of scientific notation if you wanted to. This would be 1 with 4 zeros. This would be 10,000 grams of carbon. Right? You could also change it to kilograms if you wanted to. This would be 10 kilograms of carbon. Right? So that's actually a sizable amount. That's a really big amount. Right? But that's how I get my answer. And again, everything on that worksheet is going to be the same as this. It just might be flipped, right? If you're starting with grams and you're trying to get from grams to moles, and then trying to get from moles to atoms, you do the same thing, you just flip everything, right? I'm going to get that mass, maybe it's that 12.01 grams per mole for carbon, right? And I'm going to divide this time, right? And then I need to change a mole into atoms. That's where the 6.022 times 10 to the 23rd comes into play. So it's the same idea, just flipped, right? You do all the same steps, you just do it in the reverse, and you flip all those conversion factors along the way. So you should be able to finish those worksheets. Hopefully this makes sense. Otherwise, we'll work on those things Wednesday too to make sure that we have that down. So do the best you can. Otherwise, this video should be good.